You hold your hand near a candle, not touching it, just close enough. You already know what will happen, so you pull back, but pause on what you think caused that feeling. You probably imagine heat as something the fire gives off, like a substance that flows from the flame into your skin. Get closer, more heat flows. Step back, less heat flows. That picture feels obvious, and it works, until you ask what is actually moving. Nothing visible leaves the flame and enters you. No piece of fire jumps across the gap. No glowing fluid travels through the air and into your hand. Yet your skin responds almost immediately, not just with warmth, but with damage if you stay too long. So what crossed the space between the flame and you? Was it hot air? Light? Something else entirely? And why does the same flame feel harmless from one distance, painful from another, and destructive if you touch it? In this video, we'll answer one careful question. What physically travels from a fire to your skin, and how does that process turn into burning? When you say something burned you, it sounds like you came into contact with a thing, as if fire were a material, like water or sand, that reached out and damaged your skin. That intuition is natural. It fits how we talk. You touch a flame. The flame burns you. But pause and test that picture. Hold your hand near a candle again, not touching it, just hovering in the air beside it. There is empty space between your skin and the flame. Nothing visible crosses that gap. If fire were a thing you touch, this shouldn't work. Touch requires contact. Contact requires matter, yet your skin still reacts. So the first correction we need to make is simple but strict. Fire is not a substance. It is an ongoing process. A flame is a region where molecules are rapidly rearranging through chemical reactions. Fuel molecules combine with oxygen. Old bonds break. New bonds form. That rearrangement releases energy. The flame is the visible and audible side effect of that process. Glowing gases, moving air, light being emitted. But the flame itself is not what reaches you. This matters because when you imagine fire as a thing, it hides the real question. If nothing material leaves the flame and enters your skin, then burning cannot be about contact with fire itself. Instead, it must be about something the process produces and sends outward. In physics, we don't treat heat as a material. Heat is not stuff. It is energy in motion, energy being transferred from one place to another. That means the sentence, "the fire gives off heat," is shorthand. What it really means is, the chemical reactions in the flame release energy, and some of that energy travels outward into the surrounding environment. Your skin doesn't interact with fire. It interacts with energy arriving at its surface. You can see this distinction clearly if you compare two situations. A candle flame and a red-hot piece of metal can feel similarly painful at close range. But one is a chemical reaction in gas, and the other is a solid object whose atoms are vibrating intensely. The sensations are similar because the underlying interaction is similar. Energy is being transferred into your skin, not because you touched fire in one case and metal in the other. So when you feel a burn, what your nerves are responding to is not the presence of flame. They are responding to energy arriving faster than your tissue can safely handle. At this point, we haven't said how that energy travels. We also haven't said what kind of energy arrives first, or why distance matters so much. We've only removed one misleading picture. You are not being burned by a thing. You are being burned by energy released from a process, reaching you across space. Once you stop thinking of fire as a thing, a new question becomes unavoidable. If nothing material has to touch you, then something else must be traveling outward from the flame. And whatever it is, it must be able to cross empty space. The common intuition is that fire sends out a kind of general hotness, spreading smoothly in all directions. But that picture is still too vague to be useful. It hides the mechanisms. In practice, energy leaves a flame in a small number of specific ways. Each one behaves differently. Each one matters at different distances. Let's separate them. First, there is the air. A flame heats the surrounding gas. Those air molecules move faster, spread out, and rise. If you place your hand above a flame, you feel this almost immediately. Warm air flows upward and collides with your skin, transferring energy through direct contact. This is why standing above a campfire feels much hotter than standing to the side at the same distance. The energy is being carried by moving gas, but this mechanism has limits. If you hold your hand to the side of a candle, you still feel heat, even though little hot air reaches you directly. And if you place a sheet of glass between your hand and the flame, much of the sensation remains. That tells you air movement cannot be the whole story. Something else must be crossing the gap. The second path is light. A flame emits light because the molecules and particles inside it are in excited states. As they rearrange and settle into new configurations, they release energy as electromagnetic radiation. You don't need the technical term yet. What matters is this: light carries energy, and light does not need air to travel. When light from the flame reaches your skin, it is absorbed by the molecules there. That absorbed energy increases their motion. This happens even across still air, and even through transparent materials like glass. Now notice something important. These two pathways behave very differently with distance. Hot air spreads out, cools, and rises. Its effect drops quickly unless it is flowing directly toward you. Light spreads in straight lines and weakens with distance in a predictable way. This explains a familiar experience. You can feel a campfire from several feet away on a cold night, even when the air around you is still. That sensation is dominated by energy arriving as light, not by hot air touching you. At very close range, both effects stack together. Hot gas collides with your skin, and light delivers energy at the same time. The flame hasn't changed. What changed is the rate and pathway by which energy reaches you. At this stage, we can correct another incomplete intuition. Fire does not send out an undifferentiated heat field. It releases energy through distinct physical channels, each with its own behavior and limits. Your skin doesn't care where the energy came from. It only responds to how much arrives, how fast and how concentrated it is. And now we need to look inward. Once energy reaches your skin, what exactly does it do there? So energy leaves the flame and crosses the space to your skin. Now we narrow the question. Once that energy arrives, what physically changes inside your body? Start with something concrete. Your skin is made of molecules arranged in delicate structures, proteins folded into specific shapes, cell membranes held together by weak electrical attractions. Everything works because those molecules are moving, but only within a narrow, controlled range. Temperature, in practical terms, is a measure of how violently those molecules are moving. When energy reaches your skin, it does not arrive as a single event. It arrives as countless tiny interactions. Light is absorbed by molecules and converted into motion. Hot air molecules collide with skin molecules and transfer momentum. Each interaction nudges the molecules in your skin into faster, more erratic motion. At low levels, this is harmless. Your body constantly absorbs energy from the environment. Warm sunlight, a mug of tea, another person's hand. In these cases, the added motion spreads out quickly. Energy flows deeper into the tissue, into the bloodstream, and away from the surface. The molecular structures remain intact, but increase the incoming energy, and something changes. The motion becomes too intense, too localized, too fast. Proteins begin to lose their precise shapes. Cell membranes become leaky. Chemical bonds that normally hold structures together start to break, not explosively, but relentlessly. This is the physical meaning of tissue damage. Nothing mystical happens at the moment of a burn. No special burning force appears. The same types of molecular motion are happening as before, just faster and concentrated into a smaller region than the body can manage. Your nerves detect this escalation early. Specialized sensors embedded in your skin respond to rapid increases in molecular agitation. They don't measure temperature directly. They detect the rate at which energy is arriving and disrupting their environment. That's why pain often comes before visible damage. Pain is not a report that damage has already occurred. It is a warning that the conditions for damage are being reached. This also explains a familiar contrast. You can briefly touch something very hot and pull away unharmed, but you can also be injured by something only moderately hot if the exposure lasts long enough. The deciding factor is not just how much energy is present, it is how quickly that energy is delivered and how tightly it is confined. At the molecular level, burning is not about fire. It is about organized structures losing the ability to stay organized under incoming energy. And once that disorganization crosses certain thresholds, the body cannot simply reverse it. The process is gradual, physical, and entirely mechanical. Nothing about it requires flame. Up to this point, nothing we've described is unique to fire. Energy arrives, molecules move faster, structures strain. So the remaining question is a practical one. Why does a flame cause serious damage so quickly, while many other warm things do not? The answer is not that skin is unusually fragile, and it is not that fire carries some special kind of destructive energy. The answer is timing. Your body is built to handle incoming energy, but only up to a point, and only at certain speeds. Under normal conditions, energy that enters your skin does not stay there. It spreads. Molecules collide with their neighbors. Motion diffuses deeper into tissue. Blood flow carries energy away. Sweat evaporates and removes some of it. All of this takes time. As long as energy arrives slowly enough, these processes keep pace. The system stays stable. A flame breaks that balance. Close to a flame, energy arrives faster than it can be redistributed. Not just more energy, but more energy per second, focused into a thin surface layer. This creates a bottleneck. The outermost molecules are driven into intense motion, while the layers beneath them are still relatively calm. The energy cannot spread inward quickly enough to relieve the stress. This is when damage accelerates. Proteins unfold faster than they can refold. Cell membranes lose integrity faster than repair mechanisms can respond. Chemical reactions that normally happen rarely begin to dominate. Once this tipping point is crossed, staying an extra fraction of a second matters enormously. This is why burns worsen non-linearly. Doubling the exposure time does not merely double the damage. It can push tissue across thresholds that cannot be undone. The same principle explains a counterintuitive experience. You can briefly touch a very hot object and escape injury, but holding a slightly less hot object for longer can cause deeper burns. In the first case, energy arrives quickly, but stops before damage compounds. In the second, energy arrives slowly but continuously, eventually overwhelming the same limits. Fire is especially dangerous because it combines multiple delivery paths at once. Radiation delivers energy directly to the surface. Hot gas adds collisions. Chemical reactions at the surface can begin if contact occurs. All of this concentrates energy into a region that is thin, exposed, and poorly insulated. Nothing about this is dramatic at the microscopic level. No single event causes a burn. It is the accumulation, faster than recovery, that makes the damage severe. Burning is not a failure of material strength. It is a failure of timing. Energy arrives faster than life can stay organized. At this point, the mechanics are complete. Energy is released by chemical reactions in a flame. That energy travels outward through specific pathways. Your skin absorbs it. Molecular motion increases. Damage occurs when energy arrives faster than the body can manage. Nothing in that chain requires fire. That may sound surprising, because fire feels uniquely hostile. But physically, it is not a special category of harm. Fire is one way energy is released quickly into the environment. So is a lightning strike. So is intense sunlight focused through a lens. So is friction at high speed. The outcome depends not on the source, but on the delivery. This reframing matters because it removes a hidden confusion. We often talk as if fire does something to matter, as if it carries an intrinsic property called burning. In reality, fire is only the messenger. It is a visible sign that energy is being rearranged and exported from one set of molecules to another. Living tissue is exquisitely sensitive to that transfer because it operates close to the edge of stability. Its structures work only within narrow ranges of motion, temperature, and chemistry. A small increase in energy can be beneficial. A larger one can be destructive. The difference is not moral or mysterious. It is quantitative. This perspective also clarifies something deeper. Pain is not evidence that the universe is hostile. It is evidence that your nervous system is tuned to detect when energy flow threatens organization. From the outside, fire is chemistry and light. From the inside, burning is a warning that the conditions required for life are being exceeded. Seen this way, fire does not destroy order arbitrarily. It reveals how finely balanced that order always was. The same physical laws that let molecules assemble into living systems also guarantee that those systems can be undone by energy delivered too quickly. Fire makes that limit visible, not because it is cruel, but because it is honest.